Hello everyone, we will continue with our lecture. This particular lecture will talk about pole placement observer design. As I told in the previous class, we do not have to redo the entire exercise. We will rely on the pole placement control philosophy that we studied in the last class to design observer gains and all that. So, this is let us talk about in detail about pole placement observer design. Outline of this lecture will be something like we will motivate why observer designs are necessary and some of the associated concepts. Then primarily for first half of the lecture we will talk about full order observer design, and then we will continue with what is called as the reduced order observer design. So, in this particular lecture we will talk about minimum order observer, where only one output is observed actually. That is the minimum thing that you can have. So, the general concept is valid for reduced order, but to make our life simpler we will talk about minimum order observers here. Alright, the philosophy of observer design is like this. In practice, all the state variables are not available for feedback. Remember, the state feedback control design assumes that all states are available for feedback. Okay. In practice, all the state variables are not available, and possible reasons can include something like some of the sensors may not be available, okay, and some sensors may be too expensive. So, possibly you would like to avoid those if it is feasible to work with that. And then some available sensors are not acceptable either, basically, like means it can give high noise and probably it consumes high power and things like that. So, even if sensors are available, you would like to avoid them. Okay. Primarily, either maybe it is too expensive, prohibitive cost sense, or the quality itself is not good, or the power consumptions are very high, battery will drain out very fast, like that actually. So, because of several reasons, what we think is having all sensors in the system is actually not good in a way. So, is it feasible to design a control system and make it still based on state feedback without all states being measured directly? We certainly need some feedback information, that means we certainly need to keep on measuring some information obviously, but we need not measure everything actually. Okay. So, then the state observer comes into picture, and the state observer actually what does it do? It estimates the state variable based on the measurements of the output over a period of time. That means, it does not measure only one time or something like that, you keep on measuring over a period of time, and that will contain sufficient information, so that we can recover the state actually asymptotically. Okay. And for doing that, what we need is that system must be observable, that is the condition that we need actually. So, let us talk first about full order observer design, and the full order observer something is like this, this philosophy and all that. You have a plant acting on that, okay. And then typically what you like to have is this, suppose x is measurable, okay, that means x is available, then you do not need too much of things, you can use that information, okay, as well to probably you can put a gain out here, okay, and compute your u actually, u equal to minus k x. So, take the x and then compute u directly actually. And because that is not possible in this particular case, we want to make this control operate on output feedback through state observation. So, the output is there, okay. You do some mechanism, something goes on here, we will talk about details as we go along, and then we all that we need is recover of this state information x tilde. X tilde is not really x, but asymptotically x tilde will converge to x, that is the whole idea basically. Then after this fellow converges, that x tilde converges to x, you can for all practical purpose you can keep on using x tilde actually. Okay. We will see the details of how to recover that and all, and once that is there, your control will act, this control what you see here u will act on observed states, that means x tilde actually, u becomes not minus k x, but it becomes u equal to minus k x tilde now. So, that is the difference that we are talking here actually. So, here in this particular lecture we are particularly interested how to recover this in a good way, x tilde basically, that is the whole motivation. All right. So, this lower side of the block, that is the state observer, that is what we are going to talk here actually. Okay. Remember, we need all this all the system matrices A, B we are using here, okay, and we are also using the output information Y. Okay. Everything gets used here one more time, okay, to recover the state information x tilde actually. So, let us see, I mean this plant dynamics is given as x dot equal to x plus b u, and here we talk about y equal to c x, where we especially are interested in single output to make it compatible with pole placement observer, which is like pole placement controller as we saw in the last class, are nice if you have single input system. Multi input systems are too much I mean extra things you have to do, and then they are not unique and things like that. So, here we will confine ourselves to single output systems, and then we are interested in estimating this x tilde basically. Okay. So, what do we do? So, looking at this system dynamics, we want to put almost like a artificial system dynamics, let us say, in this form. Okay. So, the where x tilde is nothing but the observed states, okay, and then x tilde dot is almost similar to that, but we have a k e times y term here actually, that is the output term what we need to keep on keep on using. Now, the question is what is a tilde and what is b tilde. I mean these may not be same as a and b. This is just that equation looks similar to what we have for the actual system, linear system of course, but need not be exactly same as that. And what is our objective here? Objective is to drive this error E is nothing but x minus x tilde. We need to drive this error to 0 actually, and once the error goes to 0, then x goes to x tilde, that is what we want to see actually, or x tilde goes to x, either way you can represent actually. So, how do you do that? Okay. So, first we need to see an error dynamics, we want to see how this error dynamics behave, and then ultimately we want to kind of design this k e, that is our ultimate objective. How do you design this k e, and how do you select this a tilde b tilde? Once you are done, then the process is over actually. So, let us see, this is E. So, error dynamic sense E is nothing, E dot is nothing but x dot minus x tilde dot, and x dot is this one x plus b u, and x tilde dot is something the observer dynamics that we are selecting. So, we will put x dot as that and x tilde dot as that. Okay. So, that is how we come to this, and then you can add and subtract a term a tilde x, okay, and we can substitute y equal to c x. Okay. If you do this algebra, then it turns out to okay, this is minus a tilde x plus a tilde x, that is coming here, and then you have another minus a tilde x tilde, okay, that is directly from there. This plus b u is from here, then minus b tilde u from there, and then this term x along that actually. So, that is direct substitution and things like that. Then you kind of combine the terms. Okay. Once you start combining, this is a minus a tilde, okay, x actually, whatever these two terms you can combine, those two terms you can combine, and things like that, these two terms you can combine and leave out that one. So, ultimately what you are looking at is this E dot, okay, is nothing but a tilde E, this is coming from here, okay, a tilde E, okay, plus this x is common to this term and the last term actually. So, I will combine these two terms a minus a tilde minus k e c into x plus this term extra term whatever is left out actually. Okay. So, this error dynamics turns out to be like that. Now, we have a freedom of selecting a tilde b tilde, that we have to kind of exercise our convenience here actually. Okay. So, how do we do that? First thing we want to make this a generic design, that means this magnitude of E should not depend on magnitude of x. I mean, suppose for example, tomorrow today you talk about let us say rocket technology where the distance is kilometers, and day after you talk about nanotechnology where x is nanometers. So, those things our E should be fairly independent of those things actually. So, in order to do that, what we want to do is these coefficients will forcefully make it 0, because we can do that here. Okay. If it is feasible to do, we will probably try to do that. Okay. So, then suppose we want to make this coefficient 0 and that coefficient also 0 to make it independent of control input also, the aerodynamics should be independent of both state and control, it should act by itself. Then the selection of a tilde is a minus k e c and b tilde is b. Okay. Once you select this, the b tilde equal to b, this coefficient is 0, and you select A tilde equal to A minus k E c, then this coefficient is also 0. So, that is how we are left out with this homogeneous system dynamics for error. As far as error is concerned, it becomes nicely a homogeneous system dynamics, and also like takes out the ambiguity that we had here while selecting this, because we now know what is A tilde and what is B tilde. We have that formula already actually. Okay. So, we have A tilde, we have B tilde, and then we put it back. Okay. The observer dynamics ultimately becomes, see, this is our formula, remember that. So, if I substitute that, it becomes that way. I have taken this minus k E c out here, okay, because this is like y tilde, c times x tilde is nothing but something like y tilde, and y minus y tilde is popularly known as residue information actually. So, you have an observer dynamics which is almost very same to what you have in state dynamics, the original dynamics, plus a gain matrix times the residue. Okay. So, using this residue information, we want to drive this error dynamics to 0, remember that. Okay. Once you drive the error dynamics to 0, x will go to x tilde, or x tilde will go to x actually. That is the whole philosophy out there. Okay. So, the observer dynamics turns out like that. So, you can start with some initial condition and keep on propagating, provided you know a value for k e which will drive the error dynamics to 0. That is our objective actually. We select a k e such that the error dynamics goes to 0, and once you have selected a k e, then this is the observer dynamics, and then you select an initial condition, guess an initial condition for x tilde, this error dynamics will guarantee that the e goes to 0 actually. Okay. So, that is how we kind of propagate this dynamics to get x tilde of t, which will asymptotically converge to x of t basically. That is the whole idea there. Now, there is a problem out here. We almost see that this terminology, if you just closely observe this error equation, okay, this is very similar to what we had it in control design. See, control design, this was our dynamics, u equal to minus k x. So, a minus b k times x, and the objective was to drive x to 0. Okay. Here the dynamics is like that. Okay. That is what we got it actually, the dynamics is like that. Okay. And then the objective is to go drive e to 0. Okay. So, it is very parallel to what we have already done. The only difficulty is here the gain matrix appeared to the right hand side, but here it appeared to the left hand side. So, we have to address that issue basically. It is not very same, it is very close to, but there is a small matrix multiplication issue out here. So, that is but that turns out to be, that makes this error dynamics kind of incompatible to this. So, visually it looks very close to, but it is still not close actually that way. But the objective remains same, objective here is x of t should go to 0, objective here is e of t should go to 0. So, for that all that we need to do is this you need to assure that this matrix that appears here, A minus k E c, is what is called as Hurwitz matrix or the stable matrix sort of thing. That means, the eigenvalues of A minus k E c should lie in the left hand side. Okay. But the great observation out here is A minus, if you see that as far as the eigenvalues are concerned, like A and A transpose have the same eigenvalues. Just by making a transpose, the eigenvalues are not perturbed. With characteristic equation lambda e minus A, whatever you do, then those terms are getting perturbed in diagonal elements only. So, A minus A transpose the eigenvalues remain same. So, we take advantage of that and tell, okay, the eigenvalues of A minus k E c is nothing but eigenvalues of A minus k E c whole transpose, just these two will remain same, and if I take out the transpose, that is nothing but eigenvalues of A transpose minus C transpose k E transpose, right. So, there is, it appears to be slightly different now, but the good thing is this k E transpose is appearing to the right hand side as what happened in the control design. Okay. So, A has been transferred to S transpose, B got transformed to C transpose, but the k whatever happened in the control design, something similar k E transpose appears in the right hand side. Okay. So, then we are kind of okay, because we know what to do actually. Okay. So, we will take advantage of that, and as I told, the goal here is to design k E such that aerodynamics is asymptotically stable, and also remember that we have to have sufficient speed of response, because as the whole idea is to decay this error very fast, and then you can do that because you are not talking about a control design. The control effort is a physical effort, here is all numerical actually. So, you can select the poles a little far away, so that the aerodynamics dies out faster. Okay. So, all these things taken into account, what we observe here is we can really work with A minus KEC transpose actually, the whole transpose whatever you do here, it A transpose minus C transpose K transpose, that is the term that we have to work with actually. Now, as we discussed in the last class, there is a nice concept of duality, we know that. So, if you consider a dual system like this, Z dot equal to A transpose Z plus E transpose V, where V is a virtual control input and then Y star is V transpose Z, then we know that the controllability of this turns out to be observability of the original matrix, okay, and that is how it appears here also, A transpose minus C transpose K E transpose actually here. Okay. So, if it is A transpose minus C transpose K E transpose, okay, so that is I mean kind of helping us to design a K E transpose first and then we know K E actually. Okay. Alright. So, pole placement design of this problem essentially yields rise to this I mean placing the poles of this matrix A transpose minus C transpose K E transpose, but then K E transpose we can visualize as something like K 0, where K is nothing but K 0 transpose. I mean this is just an artificial matrix that you can introduce, you need not also, you can directly solve for K E transpose actually. So, the characteristic equation, suppose you want to equate it directly as method 1 what we discussed in pole placement last class, then all that you need to do is you take out this A transpose minus E transpose K 0 transpose. This is the characteristic equation on the left hand side and this is the characteristic equation on the right hand side, make it equal and then select some like K 0 is nothing but K 0 1 K 0 2 like that, and then equate the coefficients of the powers of both sides and then solve for K 0 thing. So, that is very straightforward actually. Okay. So, that is what method 1 tells about. So, if it is n is less than equal to 3, then first thing you need to do is check observability, and if the observability condition is satisfied and let us assume n equal to 3 here, then define K 0 K E nothing but K 1 K 2 K 3. Remember the control gain, where control gain matrix was a kind of a row matrix in a row vector, and the observer thing the gain is kind of a column vector actually. Okay. That will be apparent to you from equation itself actually. Now, if you substitute this gain matrix back in this equation, okay, directly you can also work directly with this equation by the way, as far as equating the characteristic coefficient, I mean equating the powers of the characteristic polynomial is concerned, you can directly work with that. Okay, that is the eigenvalues, I mean that is what you need actually. So, A minus K E C you can directly work with, okay, and A minus K E C, or you can work with A transpose minus C transpose K E transpose, both will give the same eigenvalue anyway, same characteristic equation anyway. So, then that make it equal to that and then you can solve for the gain element. So, you are done actually, that is very straightforward provided we have a smaller dimension system actually. Okay. And normally these things are useful for kind of let us say you want to design a small control system for the actuator system, independent actuator system, then probably these kind of things are not too bad, because you have typically you have first order actuators or second order actuators actually, most I mean third order maybe some cases, but not more than that. So, in sometimes if you want to design a controller, separate controller for actuators, let us say these methods may be just handy for you. But in a good practical system for the entire flight control, let us say you want to design, this may fail actually, you may not, you need better techniques than this actually. So, obviously we do have better techniques, that is the method 2, okay, that is what we talked last class, that is the Bhaskara approach of control design, the pole placement control design. So, we will take advantage of that approach and then first design a K E transpose and then take transpose of that to get K E. Okay. So, let us talk about that. So, first step 1 is S I minus A, that is the characteristic polynomial for the open loop system what you have. Okay. So, you can this will give you the coefficients A1, A2, A up to An, then these are the pole locations. Okay. So, that will, if you multiply them you will get some other polynomial with that will give you alphas, and then you can follow a similar approach for pole placement design to design a KE actually. Essentially you design a KE transpose first and then take the transpose to get this final formula. This is actually nothing but the final formula actually what you get. Okay. So, where n is nothing but this observability matrix now. Okay. It will naturally pop up because this dual system what you are talking, this C transpose is coming here actually. Okay. So, this will naturally pop up as we keep on applying the formula. Okay. And W obviously we know how to form a W actually. Okay. So, n is nothing but the observability matrix which is given like that, W is given like that and KE is ultimately given like that. So, once you compute KE, the observer dynamics is like this. This is your observer dynamics where you know a value for KE now basically. Okay. And this KE is acting with error dynamics that way, which is driving the error to go to 0. Again and again I am kind of I mean emphasizing that, but you should never think that x tilde will go to 0. X tilde should go to x actually as soon as possible. Now, if x is driven to 0, x tilde will also go to 0, that is a different issue. But as far as observer is concerned, observer design is concerned, we are interested to design this KE in such a way that x tilde will approach x. Okay, so that is what. So method 2 is there, and method 3 is also we know. I am not kind of deriving or giving all the details again, but method 3 is like Ackermann's formula. So this is essentially a formula which will give you that, and once you do the algebra a little bit actually, okay, and then it turns out to be something like that, where phi a is nothing but this polynomial actually. It comes from Cayley-Hamilton theorem and all that, if you remember the last class material actually. Alright, so this particular thing is like this. Then let us talk about a small example to understand what is going on here actually. So, let us talk about a small 2 by 2 system where the A matrix and B matrix, C matrix are given like that, and let us assume that you want the desired eigenvalues to be placed somewhere here, and then you start with step 1 which is nothing but observability check. Okay. N equal to 2, so you have this observability matrix, it turns out to be this identity obviously is a full rank matrix, and hence the system is controllable, observable. And once the system is observable, you can design an observer, and then you proceed with the next thing. Okay. So, next thing to proceed, we are applying method 2 out here. So, next thing to proceed is characteristic equation of the open loop plant. The open loop plant is characteristic equations are like that. Okay. So, that gives us A1 and A2. Right, A2 is nothing but minus 20.6 and A1 is 0 here actually. Okay. So, A1 is 0, A2 is that, and then the characteristic equation or the desired characteristic equation will give us alphas actually. So, we multiply use S minus mu 1 into S minus mu 2 you do expand that, it will give you some polynomial from which you can extract alpha 1 and alpha 2. Okay. Then the observer gain matrix is given to you, I mean that is the formula ultimately. So, you just apply that. Right. So, that is how we design a observer, but remember in a exam or class or implementation whatever, computing a observer matrix is not end of the story. Okay. You also have to give observer equation, and observer equation as I told is that one that we started with actually. Okay. This is the observer equation for which we have computed a gain matrix KE, and if you want to implement it in your control design, then this observer dynamics you have to propagate in parallel. Okay, with some guess value of initial condition. Okay, and the nice thing about linear system is no matter whatever is your guess value, it will converge. I mean there is a universal convergence thing here because this dynamics as soon as this dynamics is stable, it is independent of the initial condition. So, no matter whatever is your E0, E of t is going to go to 0 as t evolves. However, it may take longer time to go to 0, and that may not be a good idea actually. It may excite bigger transients before it goes to 0. So, it is also advisable to have a intelligent guess value for the initial condition rather than just blindly using something. That is all, that always helps actually. Okay. So, this is where we are, and then okay, let us study about a nice principle that happens in linear system, for which it is this approach is very popular actually, which is called separation principle. It even is valid for Kalman filters, that is why these are very popular actually. The question here is, okay, we have a system dynamics that way, okay, but suddenly we have made u is not u is no more minus k x minus k x, but u is equal to minus k x tilde now. And we know that with this gone, okay, what is the guarantee that this u equal to minus k x tilde will give the overall system stability? It may not give that actually, that is the question, right. We make it I mean we know everything that when we design the control system, we assume that u equal to minus k x, and hence we design a control gain such that the feedback loop is stabilizing, that we discussed in the last class. Now, suddenly we are changing that to u equal to minus k x tilde. X tilde goes to x asymptotic sense, that is all right, but transient it does not go actually, right. I mean during transient x tilde is different from x. So, what is the guarantee that the overall system should remain stable, that is the question actually. So, let us answer that, let us try to answer that. So, you have this u equal to minus k x tilde, okay. So, substitute it, so that what you get is x dot equal to a x minus b times k x tilde, because u equal to minus k x tilde, and then you can expand that, okay. The x tilde is nothing but that you substitute a minus b k into x. So, what I am doing here is like add and subtract b k times x term. So, I am subtracting b k x and adding b k x also actually, okay. So, if I do that, then it turns out to be a minus b k into x plus b k into this error term actually, okay. So, because this is error term, so the closed loop system now operates based on this actually, okay. It is no more that it operates with an additional term which is nothing but b k times e basically, okay. But at the same time you have this observer error equation given this way, e dot equal to a minus k e c into e, that we just saw actually. So, if I visualize a bigger system where x and e are part of the states, okay, then what I get here is x dot and e dot, I put it together and then I visualize the bigger system operating in this way actually, okay. So, the question here is, will this bigger system eigenvalues will also be stabilizing in the left hand side, then we are done, because x will go to 0, e will go to 0 after that actually, okay. Now, fortunately it turns out that if you do a characteristic equation analysis for this matrix, then this being a block triangular matrix helps us quite a lot actually, okay. This 0 x here is a block triangular matrix for which we want determinant actually, and this determinant turns out to be this one into that one actually. So, this so what does it give us actually? So, the poles of this overall system is nothing but the poles due to controller, because this into that equal to 0 means either this is 0 or that is 0 or both are equal to 0 anyway actually, okay, right. So, I mean we want to find out the roots actually. So, in the roots of that, the entire polynomial will contain roots coming out of this equation and root coming out of this being equal to 0, right. Suppose for example, if you talk about let us say s minus 3, okay, into s plus 5 equal to 0, then the roots are s equal to 3 and minus 5 also, because that is how we are interested in actually. So, here also same thing, okay. So, this is actually like a determinant into this determinant equal to 0. So, the roots of this entire equation, whatever equations you have will constitute the roots coming out of this equation being equal to 0, that means s I minus a plus b k determinant equal to 0 and s I minus a plus k e c determinant equal to 0, right. So, once I make this characteristic polynomial, this will give me poles due to controller, and once I make this characteristic polynomial equal to 0, that will give me poles due to observer. So, that means the overall system poles contain poles due to controller and poles due to observer that we designed separately, okay. And obviously, we have designed the control system stabilizing and the observer system also stabilizing for the aerodynamics actually. So, obviously, nothing is going bad, the entire system dynamics is stabilizing in both sense actually. So, what does it tell? I mean we can essentially design a controller and an observer separately. We do not have to worry about the interaction between them, because the interaction between them is guaranteed to be stabilizing actually. Okay, that is what is very popularly known as separation principle, and that is why I mean it is also valid for Kalman filters also, Kalman filter design is an extension of this observer, LQ observer, and then we will see some of that, probably philosophy sense at least. Okay, so that is a great theorem which tells us that the control design and observer design can be done separately. You do not have to worry about the interaction actually. So, the closed loop system, I mean block diagram sense, it will operate that way. Okay. So, you will get computed from x tilde through minus k, this is nothing but the control gain actually, whatever gain you had. Okay. But this u will act both on the actual plant, and it will also act on the observer plant actually. This lower side of that is observer plant, the upper side is the control plant actually. So, u gets computed from x tilde, it does not get computed from x directly, but the way you are computing this k e makes your assures that x tilde converges to x actually, that is how it happens there. Okay. I will continue for the reduced order observer design. This is what we discussed here, is we are interested in estimating all the states basically, right. Even if part of the state is directly measured from a sensor or something, even that becomes part of the observer dynamics, right. So, even if the sensor information is actually very good for that particular state, we are neglecting that, and then we are mixing that up with everything else. So, transient sense, the entire thing is going bad actually. So, the very natural question out there is, whatever you directly measure, you do not really need to estimate. So, can you estimate rest of the things actually? Okay. So, that will take us to reduced order observer design. So, as I told, some of the state variables may be accurately measured. So, you really do not have to estimate that again, and by doing that you are not only saving computationally, you are also saving some I mean you are also making the transient behavior good, that is essentially does matter in the control design part of it. Okay. So, suppose x is an n vector, n dimensional vector, and output y is an m dimensional vector, then essentially we are asking the question that can we estimate only n minus m state variables, whatever we are observing, we will just leave it aside actually. Whatever your sensors are giving directly good measurements and all that, we do not want to make it as part of the estimation process actually. Okay. So, obviously the reduced order observer becomes n minus mth order observer. So, that is as I told, computationally more efficient, and then you have I mean transient properties may also be better actually. So, that is something operating something like this. So, essentially you are having a minimum order observer now, or the reduced order observer now, and essentially you also need a transformation thing to get it back into the x tilde part of it, because it is nothing but just putting the dynamics that you putting the states or part of the states that you already know together with what you are estimating actually. So, this is that transformation will give you that minimum order observer will give you the rest of the states, the outputs are giving you some part of the states. So, put them together and then you are getting x tilde. So, you make it your control, this is control gain. So, control becomes minus k times x tilde again. Okay. So, this transformation is not a very big deal, I mean this is very standard basically, this is just putting them together. If your y is directly measuring some states, then this is just putting them together. If your y is measuring some combination of states, then you may need a matrix transformation out here actually. Okay. So, that is why this is in general it is written like a transformation actually. Okay. So, let us study this in slightly detail. So, what we are asking here is we confine ourselves to m equal to 1, that means we have a like single output getting measured actually. Okay. So, that is what we want, and then without loss of generality we want to put that as the first state in the state order. We are claiming that the state vector x is partitioned into the small x a, which is a scalar, and the big x b, which is a vector. Okay. So, we are this entire x we are dividing into just a scalar term which is directly coming as output, that is why the C matrix is 1, and then this is actually a 0 vector sort of thing. Okay. So, this is just a scalar that is getting measured, and then there is a bunch of zeros out there. So, that will give you the output matrix actually. Okay. So, essentially what you are doing, this is this x we are partitioning into x a and x b, where x a is just a scalar which is measured. So, we are interested in estimating or observing this x b vector, that is our kind of objective here. So, the equation of the measured portion of the state, suppose you just take it, I mean this partition matrix, right. So, you just can partition here, partition here, partition here, and then you talk like that. Then you see that that x a dot, okay, is nothing but this times a times x a plus a b times x b plus b a times u. So, that is what you are writing here, okay. And so, once you write it, then x a dot, I want to take everything that I know in the left hand side, and whatever I do not know I will keep it in the right hand side actually, okay. So, this is just a different way of writing this actually, okay. And then x b dot is nothing but a b a times x a plus a b b times x b plus b b times u actually. So, that is what we are writing here actually, okay. So, also remember that a b a x a and b b u, okay, this is essentially our kind of interests here. That is what we do not know, we want to estimate that particular thing. But in that what we see is this particular term and this last term are known quantities. Okay. So, what we do not know is actually x b. So, we will try to see what we can do with that actually. Okay. So, what we have seen here, we have seen the state and output equation for the full order observer is like this, but the state and output equation for the reduced order observer can be like this. So, this is my state equation, okay, and I can consider that the left hand side what I have is actually kind of known information, right, even though I am measuring x a, but in a way I know the information of x a dot and then u also I know. So, this entire thing I can put it as some sort of a virtual output sort of thing, I consider that as a virtual output. And consider this, okay, the state and output equation for the reduced order observer is something like this. Okay, we want to draw parallels actually, that is why we want to put it here. So, if you observe this slightly closely, okay, then I can formulate this table nicely basically. Okay, this is the full order observer side and this is the reduced order observer side. So, let us see one by one. So, you see this full order observer, you are interested in x tilde, here we are interested in x tilde b, because x tilde a we know already, that is x a. Now, here we have A matrix, okay, here we have A B B matrix, okay. So, that is what we put here actually. Here we have B u only, okay, but here we have this entire term that is known to us, okay. So, this is nothing but B A B A times x a plus B B u. So, that is what we put here. Here we had only y which is like c times x, okay. Here we have this y equivalent which is something like this, okay. So, we put that one. Okay. Here we had C, here we had A B B, I mean A B. So, that is what we put C and A B B. Here we had K E which is actually a n by 1 matrix sort of thing. Here it is just one lesser n minus 1 kind of vector basically. Okay. So, this is the kind of comparison that you do with full order and reduced order. So, whatever things we know for the full order we can actually apply in the reduced order sense actually. Okay. Whatever equations we know from this side, we can directly substitute the corresponding things from this side, this table, and we can design a reduced order observer. But let us see in a little more detail. So, full order observer becomes like this. Okay. That is a full order observer equation, okay, written in a different way. You can write this minus k e c out there if you want to. So, this is a times x tilde plus b u plus k e times y minus k e c times x tilde. So, that is I mean this k e y, okay. So, what I told here is what we saw there is this particular term is shifted to that side. I mean this is okay. If you want to put it, then this will become y minus k e c times x times no sorry, this is not k is already there. So, this is c times x tilde basically, okay. So, if you want you can put it that way, but if you want you can put it the other way also. So, you can just keep it that way actually, okay. Either way you can just keep it that way, same thing as that actually anyway. So, if you want to design an observer equation, all that you need to do is you would see look back to this table and put wherever A is there you put A B B, wherever B U is there you put that one and things like that. So, if you do that, okay, I can substitute all those terms. For example, y, if I substitute y in terms of those things. So, that is what I get it in terms of y here. Okay. So, b is nothing but b sort of thing. Okay. This b u I will substitute as that one actually. So, this b u I will substitute as those terms actually that way. Okay. So, x tilde is nothing but x b tilde. So, I keep on substituting that and getting I will get this observer equation for the reduced order observer. But let us try to do a little bit simplification out here. So, x b tilde, okay, minus k times x a dot, this particular term if I take it left hand side, I am left out with all that, which I can combine and try to put them together in this way. This is just math algebra simplicity actually. Okay. So, now it can define some sort of a term which is like x b minus k e. Remember, x a is also y is nothing but x a. So, k e x a dot is nothing but this one. Suppose I want this dot out, that means it will give me x b tilde minus k e times x a. That is nothing, that is the reason why I am defining this eta term, which is nothing but x b minus k e times x a. That is a new variable eta, I am just defining that actually. Okay. And similarly, eta tilde I am defining as k b, I mean x b tilde minus k e y. And also remember that when eta goes to eta tilde, then x b will go to x b tilde, because this term will cancel out anyway. Okay. So, the whole idea here is we somehow do not want to see this x a dot term actually in a good observer equation actually. Okay. So, we are interested in observing eta instead of observing this, I mean working directly with this equation and all that. So, we want to eliminate this kind of x a dot term out here. So, by defining these two terms, you can go back and tell, okay, this is nothing but eta tilde dot now. Okay. This is nothing but eta tilde dot, this is y is nothing but x a, same thing actually. Okay. So, eta tilde dot is this term, is nothing but this right hand side what we had actually, right. Okay. So, all that term will remain as it is actually. So, we have a term from y, we have a term from u, and these two terms are kind of known to us, and this dynamics is what you are interested in. So, this is nothing but a reduced order observer equation actually. Okay. Now, we are not yet done, because this k e we need to kind of design. So, until then we are not done anyway. So, let us see that how do we formulate an aerodynamics and things like that. So, we have this radio, okay, let us go back to this equation. Okay. We have this term, okay, initially we started with this term. So, we put it back there, okay. And then x b tilde actually what is our observer, that part of the observer dynamics what we have here, okay, not that, here probably. Okay. So, we put it back there, okay. And then part, I mean if you just look at these equations and try to subtract each other, let me subtract the second equation from first, then what you get is this error which is popping up in the left hand side, and I am left out with all these, where these two terms cancel out actually. This is nice to see, this one and this term will cancel out, and you are left out with only that term actually. Okay. And so, we can do some algebra here and then tell, okay, this is what I have. So, essentially it gives me E dot equal to this matrix times E basically again, okay, where E is defined as eta minus eta tilde now. I mean E is like so this is same thing as that, by the way, this definition, when you have this difference is same as that difference actually, okay, because this is common to both. So, it will cancel out anyway. Okay. So, what I am having here is actually the same sort of thing, but the error is defined in terms of x b now, okay, or the error is defined in terms of x b minus x b tilde, but it is also nothing but eta minus eta tilde. Eta and eta tilde are defined that way for convenience, that is all. Okay. So, observer dynamics becomes like that by definition. So, if you observe eta and we know x a, then obviously x b is known to us, x b is equal to eta plus k e times x a. So, once we design k e and we have a value for eta at any point of eta tilde at any point of time, and then we have a value for x b tilde at any point of time, because x a is known to us anyway. So, we can just do the algebra there, that is the whole idea there actually. So, again the necessary condition is given in terms of observability matrix for the reduced order system. Okay. So, reduced order system observability matrix turns out to be like that, and this rank has to be n minus 1 now, because 1 is gone actually from there. The xi is not part of the output, part of the state equation. So, what we need is the rank of the matrix should be n minus 1 actually. Okay. So, again you can follow the same characteristic equation, where the reduced order matrices everywhere we have to work with reduced order matrices only. So, it will go back to the same, the partition that we started with. Okay. So, we are all working with the bottom part of the equation now, the top part is known to us anyway. I mean, the top part we are not so much keen, because xi is directly observed. So, we are not interested to use that actually. Okay. So, that is how it is. Then again the same approach you can try using your method 1, 2, 3. Either this is method 1, you can directly equate to the characteristic polynomial. Method 2, you can equate through the Vaskura formula, where W is given like that and tilde is your reduced order observability matrix, or you can have Ackermann's formula also. You can directly use it in the formula sense. Okay. So, all these tools are available to us already to us actually. Again the same separation principle holds good nicely, where you can show that the poles of the overall system are nothing but poles of the poles due to pole placement controller, and that is poles due to reduced order observer. Okay. So, that is how we okay. So, okay, let me just for complete controller. Okay. And this is observer part, this is controller part. So, that is the overall system poles are given as the poles are nothing but the same poles which is coming from the control design and which is coming from the observer design. Okay. And therefore, the pole placement design and the design of the reduced order observer also can be made independent of each other. So, you can do that design independently actually. Again, in a small example, I mean these are all just substituting and getting that right answer sort of thing. So, we have a third order system, let us say, and you have a first state is kind of known to us, let us say, okay, that C is 1 here actually. Okay. So, first state x 1 is known to us directly. So, we are interested in the kind of observing the what is x 2 tilde and x 3 tilde basically. Alright. So, we want to design a minimum order observer, assuming that the desired eigenvalues for the aerodynamics again are like that. So, the desired eigenvalues for the aerodynamics are something like this actually. So, then you can go back and substitute a characteristic equation turns out to be like that. Remember, these are all partition matrix, smaller dimensions than what we had originally. You put that in characteristic equation, okay, then expand it and you will get x square plus 4s plus 16, which is equal to 0. That means, you collect the A1 A2 from there, and then you have or Ackermann's formula you can directly use using this way. Okay. So, once you use this once you know what you are I mean this small matrices and all that, you need to compute for this gain matrix. I mean ultimately that is what you are interested in, and that will be directly given to you. You can use any method that you want really, and even method 1 will be okay here, because you are working with a 2 by 2 matrix ultimately basically. Okay. So, this is if you substitute all the things that are available to you, okay, the various partition matrices and all that for A and B, even A is 0, AB is that, ABA is that, ABB is that, then BABB is also like that. Okay. So, you can simply substitute and get a formula for get a value for the gain matrix that is acting with the reduced order observer actually. And again the computing the gain matrix is not everything. We also need to worry about the observer equation, that is what we need to propagate actually. So, stopping here is almost done the job, but only about 70-80% actually. Without that, this gain is actually useless. So, you have to find out an observer equation also, and this is the formula. Again we substitute various values, and ultimately we see that this is my reduced order observer dynamics. Okay. So, I start with some guess value for eta 2 and eta 2 tilde and eta 3 tilde, and I keep on propagating this equation along with some control which is like minus k times x basically, and this control is minus k times x tilde now, where x tilde is x1 is directly known to us, and x2 and x3 are something that we are observing actually. Okay. So, x2 instead of x2 and x3 you will substitute x2 tilde and x3 tilde, but x1 will remain as it is actually. Okay. So, that is how the state feedback control will act as far as control formula is concerned actually. Okay. So, again by substituting various values you will get you propagate this dynamics, and probably these dots are not there, again a small print mistake, probably these dots are not there here. Okay. So, this is a system dynamics that you need to propagate. Okay. And then once you propagate that, at any point of time you are getting values for this, and by definition this is that is how we are defined actually. So, we can recover this x2 tilde and x3 tilde from there. Once you know this actually, we can recover from there actually. Yeah. So, the observer state feedback equation turns out to be like that actually. Okay. So, nowhere we are actually we need, as far as operational things are concerned, we really do not operate on xi dot or y dot. Y dot is just not used by redefining this eta that way. I mean, that is the reason why we redefine eta variable that way. So, we kind of eliminated this necessity of this xi dot and all that. That is the key observation there. Okay. So, that is how we act actually. All right. And then before we conclude, there are certain comments out there. As I keep on telling, these reduced order observers are some computationally efficient, certainly, because you are acting with smaller dimension matrices actually, that is the reason. And reduced order observer may converge faster. See, the word may is important, because it is not universally guaranteed that it will converge faster. Okay. Okay, that is the reason why sometimes we tell, okay, it is also advisable to use full order observer, even if the design of a reduced order observer is possible actually. Okay, even if it is possible to design a reduced order observer, it is always a good idea to design a full order observer also together, and then see, compare which is better. Okay, then based on that you take a decision whether you buy the reduced order observer or full order observer actually. Okay. So, and there are ramifications for that as far as implementation is concerned. And also one more last comment is one more time, this poles of the observer can be far away as compared to the control. Actually, it should be far away basically, because whatever this controller gains that you are computing, based on the certain recommendations that we saw last time, that the closed loop eigenvalues or poles should not be too far away from the open loop poles, and the closed loop poles should not be too far away from imaginary axis, all those things that we discussed actually last class. Ultimately, these are realized through a control system. That means, you are paying the price for realizing that controller. But as far as observer things is concerned, you are simply computing it. I mean, this is nothing but computation. Okay. So, only thing that you have to worry about is the noise amplification part of it, because ultimately the no measurement is error free. All measurements will have some error or other, even if there are small errors and things like that, you do not want to amplify them further actually. So, for only because of that you have to restrict your gains to at some value, I mean your pole locations at some location, but other than that there is virtually no restriction actually, they are not realized through any physical mechanism. So, the poles of the observer should be far away, and the thumb rule is about at least about 4 times further from control pole locations, about at least 3-4 times further away from the controller poles, so that the error decays faster. That is what we ultimately want. X tilde should approach x as soon as possible, and that you can do that by selecting the pole locations further and further away, and only go to that level for which the noise amplification properties will not amplify basically. But other than that, there is no restriction, you can do that actually. So, that is the recommendation that is universally there. Alright, I think for last 2 classes we discussed about pole placement controller and observer along with reduced order observer, and you can see many places these are all applicable, and these observer concepts are also applied kind of rigorously in Kalman filter design. So, which is a lot more practical thing compared to what we saw today. So, this is just a pole placement observer. Then people have thought about, okay, how do we handle that very efficiently when you have multiple output information, because that is what reality is. We certainly need multiple sensors, multiple output and all that actually. and that relates to the multiple I mean this multiple input control design sort of thing, and which is very neat as far as this LQ controllers are concerned, linear quadratic controllers and all. That will ultimately lead us to LQ observer also, okay, in parallel, and then LQ observer concept will be very tightly related to Kalman filter actually. That is the way it develops that way. Okay. So, with those comments I think I will stop here for this particular class. References are like this, largely I have taken from first reference, but some good information is also contained in the second one. Okay. So, if you are interested, I think many of my material that I covered is from first book actually, as far as control design, controllability, observability and observer design using pole placement ideas are concerned actually. But some good information you can also see in the second one actually. Thanks a lot. I will stop here.